Assalamualaikum warahmatullahi wabarakatuh and good day. So in this lecture we will continue on electrostatic field in a medium week 5. So let's recap what have been touched in the previous lecture. Okay, so we study about this applied field, and you have your charged particle, and you learn about this equation, which is conduction current density. And you learn about I equals to dq over dt, and you also learn about J ds, and you also learned about this one that I told you will be covered in the next lecture, which is today. Okay, and then you also learn about from Maxwell first equation. Okay, first Maxwell equation that that we are going to use in this lecture, okay, which is the divergence of D is equal to rho V. Okay, so we will cover the electrostatic, okay, in the aspect that for conductor under static condition. Okay, we will cover conductor under static conditions. So we will do some study until we actually manage to derive this equation. Okay. Sorry for the interruption. Okay, and then we also studied about the conductors, the influence of field. Then you study about Ohm's law. We're going to measure the resistance using field theory. Okay, this is the standard Ohm's law that you know, and this is the R over VI, and this is the extended version where we can measure the resistance using field theory. Okay, so you have this as your equation for resistance, and you also have this for equation of resistance. Please refer to the previous lecture. Okay, so now we go to the next is conductor under static condition. Okay, okay. Here, in the previous lecture, I briefly touched about this. Okay, here is actually the situation where the conductor having applied in static condition. Okay, under static condition. So here your rho v will become 0, and then this rho v will change to the surface charge because the charge will accumulate at the surface. Here you have negative, and here you have the positive. So from rho v you will have rho s. Okay, so for conductor under static condition, imagine that we have a conductor, okay, of a certain conductivity, and we have a charged particle inside initially. Okay, initially we have a charged particle inside, which is rho v. Okay, when we don't apply any field yet, and then we have this one, we have a charged particle, and this was the electric field. Okay, so this is applied field, and this is a charged particle. Okay, so initially the rho v, okay, when the time is not equals to 0, okay, or less than 0, so we have rho v is equals to rho v naught, means this is the initial condition of rho v naught. Okay, if you see from my previous lecture, we have this equation, right? So you try to derive this having from this situation. Okay, conductor under static condition. So you will have a rho v here, okay, and with respect to time. Okay, so we start from the continuity current equation. Okay, so you have the rho and the divergence of J is equals to negative D rho V dt. Okay, so this is one of the current model. Okay, you see you have this as the continuity current equation. You also have this I eq dt. You also have this J equals to sigma E, and you have I equals to J ds. So you have a lot of equation for current, so you have to know which one to be used. Okay, so here is from the continuity current equation. We try to replace J. Okay, here we have the J is actually sigma, we can put outside because it's just a constant. Then you have your E. Okay, then you have negative rho dv of your dt. Okay, then you know that from your first Maxwell equation, okay, from your first Maxwell equation, you have you know that divergence of D equals to rho V. Okay, then you know D is actually equals to epsilon naught E, right? So you can put epsilon naught E equals to rho V. Okay, then you come to rearranging. You do the rearranging, then you have okay. So we try to make this equation become the main part, or the left hand side, and this one is to be the remaining part. So we bring over this to the side. Okay, so now this one okay, we take out the dt, we bring dt there. Okay, with the negative sign, and this negative rho v dv, we this one carry on here. Okay, and then after that rearrange the parts, then you have okay. Then after that, when we try to apply the integration, okay, when we apply the integration, you will have this as a ln, okay, as a ln rho v. Okay, then you have integration of this will result in the value of this. Okay, t, and then because it is integration and we don't have limit, we should have a constant. So the constant here we can take as a ln rho v naught. Rho v naught is value of rho v, volume charge density at the time of 0. Okay, so taking this into epsilon form and taking this into the exponential form, so rho v equals to rho v naught e negative sigma epsilon naught and t. Okay, so at time t equals to 0, okay, at time t equals to 0, so this is your 0. Okay, at time t equals to 0 here, so you will have the highest value, okay, which is here, which is rho v naught. Okay, after that, following the time, due to this, you see this is negative exponential, right? So you will have an abrupt decrease. Okay, so this is your 0. So electric field applied, okay, at this time is not equal to 0. Okay, when the t less than 0. Okay, so because we have electric applied after the t. Before we apply the applied field, there is still rho v. Okay, but when we apply the electric field, the rho V will become rho S. Okay, so means at t greater than 0 there is applied field, because of this applied field that our rho V has become rho S. Okay, rho V will become rho S under the applied field. Okay, influence of applied field. So you get this equation, which I said that I will cover. So you guys can refer to, let me see. Okay, you guys can refer from page 184 and so on. Okay, 184 and above. Please have more reading so that you have more information and more detailed explanation. Okay, so okay, what happened in conductor? What happened when this conductor under static condition? What happened? The first is that our rho V, okay, when we already applied the field, our rho V will become 0. Okay, and then our rho V will converted to rho S, because under applied field, we will have charge here. Okay, at the end, and the other surface we will have a positive charge. So this will contribute to value of rho S under applied field. Okay. Next, due to there is no rho V, okay, so electric field intensity inside is 0. Okay, for the case of conductor under static condition. After that, for conductor under static condition, you will have del V is equal to negative E. Okay, at this page of 185. Okay, so a conductor is called an equipotential body, implying that the potential is the same everywhere in the conductor. This based on the fact that vector E equals to negative divergence V equals to 0. Okay, so you guys can have more reading for more better understanding. Okay, so this is what happened in the conductor under static condition. Okay, rho V 0, rho V will change to rho S, electric field intensity is 0 inside, and then rho V and the divergence of V equals to negative E. This is the concept we call okay. So with that, I hope that you guys understand. So this is about the conductor under static condition. So the next that we will cover is based from the lecture slide. Okay, we will study about the boundary condition. Okay, the boundary condition. Okay, the next part is the electrostatic boundary condition. Wait, I try to see the slide. Okay, so we are in place. Okay, we are following the lecture slides. So we will continue with the other lecture, okay, which is conductor in dielectric boundary condition and introduction to the concept of capacitance. Okay, So we have covered, okay, we have covered this, okay, in the last lecture, and we also cover this where you obtain your resistance from field theory approach, and then you know about the conductor under static condition. Okay.